Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 3. Nonlinear Linearizable Least Squares Regression. Many real-world relationships between variables are nonlinear, but we can often apply transformations to make linear those relationships that are referred to as linearizable models, i.e., not every nonlinear model can be linearized. Regression of linearizable models is a technique that involves fitting a nonlinear model to data with the help of a mathematical manipulation or transformation. The model is transformed into a linear form, allowing for the use of linear regression to estimate the model parameters of the original nonlinear model. However, it is important to choose the right transformation and ensure the model is truly linearizable to achieve accurate results. The approach of linearizing a nonlinear model and then fitting it using linear regression is a particularly useful technique because linear regression is easier to understand and implement and is more computationally efficient. Linear models are easier to interpret because the relationship between the independent variables and the dependent variable is additive and directly proportional. This clarity allows for more intuitive understanding and communication of the model results. By transforming a model into a linear form, the complexity of the model can be reduced, making it less likely to overfit, especially when working with small datasets. Datasets that are suitable for linear or nonlinear models are usually subjected to an appropriate transformation to obtain a linear or polynomial model. For example, following models can all be transformed to linear models by making suitable substitution for certain terms or components. Transforming variables in regression is a technique applied to improve the linear model and the data, and to meet the underlying assumptions of regression analysis. A successful transformation model can better satisfy the assumptions of normality, linearity, and homoscedasticity. Confidence intervals computed on transformed variables should be recomputed by transforming back to the original units of interest. Models, goodness of fit, etc., can only be compared to the original unit of the dependent variable. Most physical events in science and engineering are nonlinear in nature, and an observed nonlinear dataset should satisfy pertinent theoretical relationships. Some of the most common nonlinear models can be easily linearized or transformed. Most common linearizable models are classified into three categories: power law model, exponential growth or exponential decay model, saturated growth or saturated decay model. There are many more nonlinear models, some of which may or may not be linearized. A nonlinearizable model results in nonlinear relationships between model parameters, which can be complex and can require sophisticated techniques to obtain a numerical solution. To be able to come up with a suitable regression model for a given dataset, it is necessary to understand how the basic nonlinear models behave when the model parameters are changed. Some physical quantities encountered in a wide range of science and engineering fields are related by the power law model. It is also suitable for cases where the underlying model is unknown. The power law model depicts a concave down increase for positive b's, with b less than 1, and a concave up increase for b's greater than 1. For minus b's, as exponent, the curve goes to 0 asymptotically faster for b greater than 1. A significant number of physical laws are also represented by an exponential growth or exponential decay form. If the model parameter b is positive, the model depicts the exponential growth. The larger the parameter b, the greater the growth is. For minus b's, on the other hand, the model predicts much faster exponential decay with increasing value of the parameter b. Both models, generally observed in chemical reaction kinetics, depict saturated growth rate or saturated decay rate under limiting conditions. Y equals ax over x plus b is the saturated growth model. For small values of the parameter b, between 0 and 1, saturation value is quickly achieved. A much longer time period is required for larger values of parameter b to reach saturation. Y equals over x plus b is the saturated decay model. For small values of b, the initial change is sharp, but then decays quickly. When it comes to linearization procedure, both power law and exponential growth or decay models are linearized by taking the logarithm of both sides. The natural logarithm of y is defined as uppercase Y. Uppercase X, A, and b can be identified by comparing to the model equation y equals a plus bx. Saturated growth or decay models are linearized by first inverting the models. 1 over y is set to uppercase Y, and similarly, uppercase X, A, and b are identified by comparing to the linear model y equals a plus bx. In this example, we consider the problem of experimentally determining the activation energy of a chemical reaction. The theory of chemical reactions dictates that the relationship of the reaction rate constant, K in m per s, with the reaction temperature, T in K, obeys the Arrhenius equation, where R is the gas constant and K is a constant. Use the experimental dataset presented below and apply least squares regression to the Arrhenius equation to determine the activation energy and the reaction constant for the chemical reaction in question. The Arrhenius equation is a nonlinear equation, which can be linearized by taking the natural logarithm of both sides as follows. We identify the new variables in the transformed system, uppercase X and Y, which has resulted in a linear model. The original dataset needs to be transformed to a set of xi and yi's as follows. Next, we need to transform the original dataset also into a set in the transformed system. Once the model parameters a and b are found, we can obtain the actual model parameters k and e sub a as follows. To begin, we first tabulate the original dataset by assigning subscripts. The 2x2 system of equations for the linear regression requires the sum of x's, y's, x squareds, and the product of x, y's. To obtain these quantities, we complete the table as follows. Substituting the pertinent quantities into the linear system, we get. Solving this linear system gives a and b as 23.3993 and minus 269.177, respectively. We can then find the model parameters k and e sub a as follows. To calculate r squared, we need to find the sum of the squares of residuals and the sum of the squares of the mean deviation, which we find as follows. Finally, r squared is obtained as 0.98032. Here we have the transformed xy data and the linear fit plotted together. We observe that the data points are clustered along the best fit line. An average confidence interval can be determined once the RMSE is calculated. The RMSE value is 0.163, and all data remain within 95% confidence interval. Now we turn our attention to the original data and the nonlinear regression obtained. We can then write the best fit curve as follows. The sum of the squares of residuals and the sum of the squares of the mean deviation for the original data and the nonlinear best fit curve are obtained as follows. Finally, R squared is obtained as 0.97852. Note that this R squared value is, as expected, different from the one calculated using the transformed dataset and the linear model fit. Here we have the original dataset and the nonlinear curve fit plotted together. We observe that the data points are clustered along the fitted line. An average confidence interval can be determined once the RMSE is calculated, which is 7.72 times 10 to the 8. The 68% confidence interval and 95% confidence intervals are illustrated on the figure. Note that all data remain within 95% confidence interval. The PO plot depicts data points lined up along the 45-degree line. The linear regression for the observed predicted data gives a very small intercept, 0.00409, and a slope of 0.999, which corresponds to an angle of 44.98 degrees. The R-squared value of this regression is 0.97852. We can conclude that the exponential model suggested for the experimental data is suitable, and it has a strong prediction capability. With this note, we conclude this video session. That is all for now. See you next time with another topic. Bye.